So what we have here in section 11.1 is the study of sequences. And it's not going to finish in this section, it's just going to start in this section. Now, a sequence can be any list of numbers, and I've got 3 different ones. This first one doesn't really have much of a pattern. There is actually an application for this. I'll tell you in a minute. The second one is a little bit more predictable. In fact, can anyone predict what the next term here would be? What would be the next term?
Negative 1 over 16.
Nice, negative 1 over 16. How about down here? A little bit more difficult. Can anyone figure out the next one there? I'll give you some help. It'd be 720. Yeah. So what's going on? Well, the first one is just the number of new cases of the coronavirus in Michigan, starting on 3/16. So, and this was a scary jump when that hit us, but it'd be nice if we had a formula to predict this. It'd be nice to see that go down. But what we'd like to know is, what's the long-term behavior of this sequence? Is it going to go up? Is it going to go down? Is it going to be stable? What's going to go on with that? And the same thing is true for these other sequences. We want to know what's happening to them. Are they increasing, decreasing? Are they settling down? Do they add up to something? That'll be the next section when we look at the sum of these things. And the sum of a sequence is going to be a series. But for now, let me give you some notation here. So a lot of times we'll give the sequence a name, call this sequence A, and then the individual terms in this sequence, we'll give them subscripts, A sub 1, A sub 2, A sub 3, A sub 4, and so on. And down here, maybe I'll just give this one a different name, B sub 1, B sub 2, B sub 3, and so on. And what would be nice for these terms, for these formulas here, for these sequences here, it'd be nice if we had a general formula. And in these 2 cases, we can actually write down a general formula. Now this one down here would be A sub n is going to be 2 times negative 1/2 to the n minus 1 power. You might recognize that as a geometric sequence from your college algebra classes. The one down here is always been a fun one for me. Another way to write this is 1, and then 1 times 2, and then 1 times 2 times 3, and then 1 times 2 times 3 times 4, and so on. And in math, they have a fancy name for this kind of stuff. It's called a factorial. And this would be 4 factorial and 5 factorial. And actually your calculator has a way to calculate these things pretty nice. Now, if this was an English class, do you know what that would be? 5! But it's a math class, so it's 5 factorial. And let me show you where to find this one. Now, usually that's something that's pretty fun in face-to-face class, wakes people up. I'm hoping that it woke you up a little bit as well. But to find this on your graphing calculator, let's first type the number 5 and then hit the math key and then go over to probability. The 4th option down allows you to do a factorial. So 5 factorial is 120, 6 factorial is 720. But factorial is a number that gets amazingly big, amazingly quick. 5 factorial would mean that if I had 5 students and I wanted to seat them in order in a row of desks, then I could seat them in any of 120 different ways. So, wow, that's a lot. If you had 10 factorial, that'd be the number of ways that I could arrange all the players on a starting roster of a baseball team, plus the manager along the first base line. Let's take a look at 10 factorial. Anyone want to guess what that would be? It's over 3 million, 3.6 million different ways to arrange a mere 10 collection of 10 objects. So that's, wow, it grows really big, really fast. We'll keep an eye on factorial. Now, some of the problems that they ask you to deal with in this course or in WebAssign are simply just to list out a few terms. And I kind of really struggle with this in terms of assigning homework, because I am asking you to grade or to do this for a grade, but sometimes they go overboard and they ask you to like list 10 terms with 5 digits of accuracy. And I don't know. Some of them are good problems, but I really struggle with that. At least in this example, things are a little bit sane. So this is the general formula for a sequence. A sub n is -1 to the n minus 1 over 4 to the n. And they ask you to list the first 5 terms. Well, that shouldn't be too bad. I'm not sure we'll need a graphing calculator for that or not. We actually can benefit greatly from a graphing calculator. Depends on, you, if you want to use it or not. So let's see. A sub 1 would be -1 to the 1 minus 1 over 4 to the 1, which is -1 to the 0 over 4, which would be 1/4. Okay. A sub 2, -1 to the 2 minus 1 over 4 to the second power. Well, this time I'm going to have -1 to the first power, which is just -1 over 4 squared, which is 16. And after a little while, maybe you'll see a little bit of a pattern here. A sub 3, -1 to the 3 minus 1 over 4 cubed. That's going to be -1 squared, which is +1 over 64. And if we start listing these things, then maybe that pattern will become a little bit more clear. 1/4, -1/16, 1/64. Can you see the next 2? What would they be? Well, to get from one to the next, you're multiplying in the denominator by what? 4, right? Multiply by 4 in the denominator, so 4 times that is 256. And in the numerator, you're multiplying by -1. So a sub 4 is -1 over 256. See if you can't figure out a sub 5. What am I going to put in the numerator?
1.
Yeah, +1. And 4 to the 4th power is 1,024. Or multiply this by 4. Same thing. -1 to the 5 minus 1 over 4 to the 5th power. And that's not bad. Look, you can do these things pretty quick. But, technology can make this a little easier if you're interested. So the question is, are you interested?
Yes.
Oh, he saved you. You're about a second away from doing this by hand. All right, well done. So this is going to work on the TI 83 and 84. It works better on the 84. I'm hoping that no one's stuck with an 83. Let's see. So on the TI 84, you're going to want to use the sequence command. SEQ, this command. And I only know one place to find it, but it has the form, this sequence of whatever expression you want, and then the variable that you're using in your expression, the beginning and the end, and then an optional increment. And there should be a right parenthesis there, but I've kind of ran out of room. What would that look like for this example? So for the above example, for example A, you could do this. It'd be sequence of -1 to the n divided by 4 to the n. That would be your expression. What's the variable in that expression? Don't think too hard.
Is it 5?
The variable.
Oh.
The variable would be n. You're going to begin at 1 and end at 5. Maybe that's what you're working there. And that's it. So the question is, well, where on earth do you find the sequence command? There's probably a better place to find it, and I'm sorry that I don't know it. But we're going to do two things here before we do, or we're going to do one thing before we find the sequence command and type this in. And the one thing I want to do is I want to change the mode of your calculator. See, it's not enough that we've used function, parametric, and polar. We've got to use this last one for sequence. So you hit the mode key, you go down a couple, and then over to the right for sequence and press enter. Now, if you look on the face of your key that says X, it also has T, theta, and N. So that's going to be for function, parametric, polar, and sequence. So now when I press this, instead of getting an X, I'll get an N. Okay, that's fine. You can hit second and then mode to quit out of that. To find your sequence command, we're going to go to the catalog, second, and then 0. And you see a long list of commands, a huge list of commands. And boy, you got a long ways to scroll down, don't you? Well, I'm going to show you a shortcut. Up here in the upper right-hand corner, it says A. Basically, what they're saying is we've already pressed this alpha key for you. So if you want to jump to a letter, like, I don't know, S, we've already pressed alpha for you. All you got to do is press the S. So if you press the LN key, it jumps you down to the start of the S's, which makes it much, much easier to get to the sequence command. And I'll just scroll down a little bit until I see the sequence command.
There's another spot you can find it.
Where is it?
So if you hit second and then stat.
Say the list, yeah. Okay.
And then go to ops.
There's one other cool thing that I'll do while I'm here. If you're looking at a command, you're like, oh God, I don't know how to use this thing. If your calculator's got an up-to-date operating system, you should be able to just press the plus key. And it'll show you exactly everything that I showed you just now. Now, because I did that, I'm going to hit the trace key, which will paste this into my calculator. And then let's type in our expression. Left parenthesis, -1. Raised to the nth power, n minus 1, right? Is it n minus 1? Yeah, it should be n minus 1. I wrote down nth power in my example. I'll get out of the exponent, so let's go to the right there. And then comma is right above the 7, comma, n, comma 1, comma 5. And that should generate my sequence. Whoops. I forgot something. I forgot to divide by 4 to the n. So if I hit second and then enter, and just go back and do this again. Divided by 4 raised to the n. And then comma n, comma 1, comma 5. That should do a little bit better.
Ooh.
Ooh, yeah, good job. Bonus points there. Thank you. Now, the real cool thing, though, is turning these into fractions. If you hit the math key and press enter twice, all right, let me hear that again. Ooh.
Ooh,
Yeah, there you go. So there's our answers. I mean, how cool is that? It's just giving you everything. Now, let me, it might have been Amar, somebody reminded me how to get to the sequence command a little bit easier. It's underneath the stat menu, if you hit the list menu, essentially. So let me clear this out. I'll do that again for the list menu, a little easier way to get there, I hope. So second stat, you want to go over to ops, and then the 5th option down is sequence. Oh, this is menu driven. That's even better. Wow. So I'll clear that out. -1 raised to the n minus 1. Oops. You might notice I need parentheses around the n minus 1. N minus 1, parenthesis, divided by 4 to the n. The variables n, got that. Start, 1, and 5. And step, this time we'll do 1 the first time. We'll come back and do maybe 2 the next time. And then when you're ready, you paste that. And look, that menu-driven thing turns into the exact same thing that I just did for you using our sequence command off the catalog menu. Bam. Beautiful. So the one difference between what we did and what they did is that they put this 1 here. If I hit the second key, then the enter key twice, I can go back 2 commands. Let's just change that. Instead of going up by 1, let's go up by 2 and see what that does. So I start with the first one, and basically means I skip 1 and then go to the third one, and then skip 1 and go to the 5th one. So I got 1, 3, and 5 here because I'm stepping up by 2, my values of n, instead of stepping up by 1. 1 is the default, so if that's what you want, you're in great shape there. All right, let's actually get back to the calculus. I don't really like to take such a diversion into the calculator, but it just makes it so easy. Oh, some feedback. Is that a good diversion?
Yes.
Okay. All right. Cool. Thank you. Appreciate the feedback too. All right. So let's do another one. This is going to be a recursive sequence. So for those of you who ever take a programming class, recursive programming is really powerful. Recursive sequence. And it works like this. A sub 1, they have to tell you. They have to tell you the first one. A sub 1 is 1. A sub n plus 1 is 5 times a sub n minus 6. So this is not an explicit sequence. I can't just plug in, and find the 20th term in the sequence. Like with this one up here, I need to put the minus 1. I can find any term in the sequence I want. You want the 100th term? Plug in n equals 100. You want the 1000th term? Do likewise. But here, things are different. All I know is how to get the next term once I have the previous term. So if I have the 10th term and I want to find the 11th term, I'm okay. I start out with the first term. To get the second term, a sub 2 is going to be 5 times a sub 1 minus 6. So I'm putting in n equals 1. 1 plus 1 is 2. So if I have the first term, I can get the second term. So it's going to be 5 times, well, the first term is 3. So I get 9. That's a sub 2. Now that I have a sub 2, what else can I find? If I have a sub 2, I can get a sub 3. So I'm feeding back into this system. A sub 2 was 9. So 45 minus 6 is 39. See if you can't find the next two terms in this sequence, a sub 4 and a sub 5. Like I said, this is a recursive sequence. They're pretty cool. They're very, very powerful. Okay, so let's see how we're doing here. So the next term, the fourth term is going to be 5 times the third term minus 6. So 5 times 39 minus 6 gives me what? That'd be 189?
Yeah.
Thank you. And then the fifth term is going to be 5 times the fourth term minus 6. So the relationship is that this is always going to be the next term. If I want the 7th term, I got to have the 6th term. If I have the 6th term, I can get the 7th term. That's the relationship. So this last one would be 5 times 189 minus 6. So that's what, 945 minus 6, 939. Okay. So there's your first 5 terms of this recursive sequence. Now, like I said, this can be very, very powerful, but it's also at the same time, you know, really tedious if you have to do this stuff by hand. Fortunately for us, computers are really well suited to doing that kind of tedious work. Let me give you another one like that. Another recursive sequence. So we'll call this example C. A sub 1 equals 7. A sub n plus 1 equals a sub n over 1 plus a sub n. And there we go. Let's get that focused. I'm sorry, I didn't give a chance for people to ask questions on the last one. Is there any misgiving on example B? Previous one? Doing okay with recursive sequence there? This is another recursive sequence because instead of, defining, a sub n as some function of n, I've got the function or the terms of the sequence are defined in terms of itself. So it's, again, a recursive sequence. Well, let's try a couple of them. A sub 2 is going to be a sub 1 over 1 plus a sub 1. Well, at least the first one's not too bad. That's going to be 7 over 1 plus 7, which is 7 over 8. Now, for some of these, it might be beneficial to take out your calculator and work your way through them. A sub 3 is going to be a sub 2 over 1 plus a sub 2. What should I put in here? Anyone?
7 over 8.
Yeah, 7 over 8. 7 over 8 plus 1 over 7 over 8. I highly suggest that you not spend too much of your time trying to deal with the arithmetic here. You should be able to do it. I'd love for you to be able to do it, but I love even more that you get the right answer here. So let's just do this on our calculator. I'll type parentheses 7 divided by 8, parentheses, divided by, parentheses, 1 plus 7 divided by 8, close parenthesis. Then I'll hit the enter key, and then I'll hit math, and then press enter twice. And oh, I get 7/15. Hey, great, that's my next one. So 7 over 15. So that's a sub 2, pardon me, a sub 3. Let's find a sub 4. For a sub 4, I'm going to put in a sub 3 over 1 plus a sub 3. So it's going to be 7 over 15 plus over 1 over 7 over 15. Now, if you're a little tired of working with fractions like that, you're like, I just don't like working with those fractions. There's a couple ways around that. I could take 7 divided by 15 and store it in x. So it's going to look like that. And then to calculate this one, I'll just type in x divided by parentheses 1 plus x. And then I'm going to play the same game that I did just a minute ago, hit the math key, answer the fraction, 7 over 20 seconds, or 7 over 22. And why don't you tell me what the last one is?
7 over 29.
Yay. 7 over 22, 7 over 22, and a 1. So we'll plug those in there. And yes, 7 over 29. Okay. Did anyone actually catch the pattern here? I don't know. Maybe you caught the pattern. You just came up with that pretty quickly.
Yeah.
See it?
You just add 7 to the denominator each time.
Yep. That's all you're doing. You're adding 7 to the denominator each time.
I have a question. So when we catch on to the pattern, like after doing it 2 or 3 times, can we just do the rest that way, or do we need to show it out?
You can do the rest that way. Yes. C. Yeah, you know, after you catch a pattern, I don't see any real point in making you do it much more. So, yeah, go for it. Let's take a look at some examples where we're actually asked to find what these terms are. Now, by the way, let me just give you a quick example of a recursive sequence. And it's Fibonacci sequence. 2n, no, 1n, and then 2 C's, I think. Fibonacci. So he's over here. Fibonacci was an 11th century mathematician. I'd love to spend hours talking about him. Let me just talk about the one problem that he's known for, he's very famous for, is considering the number of breeding pairs of rabbits. If you have one pair of rabbits and they breed, and after a month they have an offspring who can also breed. After 2 months, you've got 2 new rabbits, so now you got a pair. And then they can start breeding, etc. The sequence of rabbits that you get, number of rabbits after you get, increases like this. And it turns out to be a recursive sequence. So let's see, Fibonacci sequence would look like this. Well, f sub n equals f sub n minus 1 plus f sub n minus 2. So f sub 1 equals 0, I assume f sub 1 equals 1, and f sub 2 equals 1. So it's actually a pretty cool sequence, and you'll see it in applications like stock picking. They use Fibonacci retracement. And it comes up in a lot of unexpected places, like the number of seeds in a sunflower. But the sequence would look like this. 1 and 1 is what you start out with. But then to get the next term of the sequence, you add the previous 2. So 1 and 1 gives you 2. 2 and 1 gives you 3. 2 and 3 gives you 5, 8, 13, etc. So that's your Fibonacci sequence. Really, really amazing stuff. Sorry, we can't do more. But let's look at, we'll call this one example D, previous example not counting. Example D of a sequence that looks like this. -9, 6, -4, 8/3, -16/9, etc. So, okay. Well, you might hazard a guess to look at this and say, you know what, it looks like I'm multiplying by something to go from one term to the next. So let's form a ratio here of 2 adjacent terms and see if that idea holds water. So if I look at 2 adjacent terms, I get 6 over -9 reduces to -2/3. Okay. Let's look at 2 more to go from here to here. Again, looking at the 2 adjacent terms, the latter divided by the former, -4 divided by 6 is again -2/3. So wow, that -2/3 is what's called your common ratio. And you can check that it's consistent for all of these things. So this is a geometric sequence. And the geometric sequence has a general form like this. A sub n equals a sub 1 times r to the n minus 1 power. That's the general term in a geometric sequence. What's a sub 1, do you think?
-9.
Yep, a sub 1 is just your first term. So it's going to be -9, thank you very much, times -2/3 to the n minus 1 power. Beautiful. There's your geometric sequence. And that's the general term in that. We can get any term from that. Let's just check that it actually works. I'll go over to the list menu on my calculator, go down to sequence, and we'll fill in everything and see if it works. So our expression is going to be -9, parentheses, -2 divided by 3 raised to the parentheses, and well, I'll just use x minus 1, since my calculator doesn't happen to be in sequential mode. Variable will be x, start at 1, and we'll go 6 terms, step of 1. Something like this. So it's looking pretty promising. We do our little math menu trick, and hey, that looks exactly like it's supposed to, right there. So we can feel pretty good about our general expression. All right, well, I hope you enjoyed geometric sequences. Let's work with an arithmetic sequence. 2, 5, 8. I'm hoping that after just a few numbers like this, the next term should be pretty clear. What will be the next term? Yeah.
11.
Yeah, there you go. Thank you. Arithmetic sequence has a general form like this. A sub n equals a sub 1 plus n minus 1 times d. Now, in a geometric sequence, we are multiplying by a common ratio to get from one term to the next. What are we doing to get from one term to the next in an arithmetic sequence? You're adding. So D is your common difference. A sub 1 is your first term. So the general term here is going to be a sub n equals 2 plus n minus 1 times 3. You could, if you wanted to, simplify this to 2 plus 3n minus 3 or 3n minus 1. But I like this term better. From here, I can see exactly what the first term is, and I know what the common difference is. And writing it like this just screams out, oh, this is an arithmetic sequence. This will give you the same things. No problem there. It's just aesthetically, this one looks pretty good, and it makes it very, very clear that it's an arithmetic sequence. Now, at the start of this, we started with some examples of sequences, and one of them was, the number of cases of the coronavirus in Michigan. And I was asking, well, it'd be nice to know where this is going. And that's not only true of this sequence, but it could be true of lots of sequences. We want to know what's happening to them as the number of terms approaches infinity. Are they going to converge to something? Are they settling down to some number, or are they just growing wildly? What's their long-term behavior? So as n approaches infinity, what's going on. So we're going to look at that a little bit and try and make some headway figuring out what happens to these things with, I'll do example F. A sub n is 7 plus 4n squared over 5 plus 3n squared. Does A sub n converge? And essentially that means, does this have a limit as n approaches infinity? Does it settle down to something or not? So let's find out. Let's take a look at the limit as n approaches infinity of 7 plus 4n squared over 5 plus 3n squared. Now there's a couple ways you could work this one. Let me see what you got.
7 over 5.
Nope, but I appreciate that. I think you might be on the right track. So if the degree of the numerator and the degree of the denominator are both equal, then you can just look at the ratio of the leading coefficients. So you can just look at 4 over 3, and that's it. So it converges. There's another way that you could do this one as well, and that's other than remembering your rules from college algebra. What's the calculus way to do this one? Or what's one calculus way to do this one?
L'Hopital's rule.
L'Hopital's rule, yeah. So this would equal the limit as n approaches infinity. Now I can apply L'Hopital's rule because this limit in the numerator is going to infinity, and same thing in the denominator. So if I apply L'Hopital's rule, then I can take a look at the limit of the derivative of the numerator and the derivative of the denominator. So it'd be 8n over 6n. And guess what? I still have to apply L'Hopital's rule again, or at least I could. It's still going to go to 4/3. These can cancel. So, hey, so it converges. This term does eventually settle down to something nice and stable, finite. Okay. Sample, we're just on G now. What's the limit as n approaches infinity of 8n minus 1 factorial over 8n plus 1 factorial? So this is that stuff that I mentioned earlier. Now, the thing about factorial is you kind of got to remember what this means. So let me come over here and remind you. N factorial is n times n minus 1 times n minus 2, n minus 3, da, 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 all the way down to 3 times 2 times 1. Eight n plus 1 factorial can be written as 8n plus 1, and then when I subtract 1, I'll get 8n. And then when I subtract 1 again, I'll get 8n minus 1, all the way down to 3 times 2 times 1. Now, the part that I want to draw your attention to is this right here. I can write this as 8n plus 1 times 8n times 8n minus 1 factorial. That's the part that we need here. So let me pause. If you're a little unsure of that, then let me help out. All right. So with that in mind, let's rewrite this limit as the limit as n approaches infinity of 8n minus 1 factorial over 8n plus 1 times 8n times 8n minus 1 factorial. You see where this is going. You see why we took out and rewrote that denominator. We get a nice big cancellation here. And so that leaves me with the limit as n approaches infinity of 1 over 8n plus 1 times 8n. And that's going to go to 0 because the denominator is going to get infinitely large, dividing into a fixed numerator. So, okay, let's stop things here. Any comments or thoughts on those last couple there? All right.